Hi, my name is Ben, and this is a sort of rerun of a talk I gave to the Mathematics Student Society back in September. And it's about Benders Decomposition, which is a mixed integer programming technique. It's taught in Math 3205. Um, so let's start with a bit of a motivating example. Um, Classically, this example is called the uncapacitated facility location problem. But imagine that we own an amount of grocery stores in some area, and we want to build some warehouses to supply the grocery stores. Um, we identify some possible locations to build the warehouses, and we can, calculate the cost of building each warehouse and then the cost of supplying each store from each possible warehouse. And effectively, what we want to know is what's the cheapest way to supply all the stores. So we want to build up any number of warehouses we want and connect the warehouses to the stores so that the overall cost of the building and the supplying over some period of time is the cheapest. So this is a bit of a diagram for what the situation could look like if you've got 30 stores and 30 potential warehouses. Um, and so we can sort of formulate this as a linear programming problem. In general, a linear programming problem is a problem of this form, where we're trying to minimize some cost vector times a vector of variables. Subject to a set of constraints, and the constraints are all linear. So it's a matrix, A times X less than or equal to B. Usually we write each row of the matrix out sort of separately because they mean different things, but you can compress it into matrix form. And in general, we want our X's to always be positive or zero. Yeah. Cool. If we can convert a problem into sort of the linear programming form, then we can solve it using something called the simplex method or simplex algorithm. And we can solve it actually to optimality, which is pretty important for a lot of problems. Oftentimes, we want to restrict the values that our variables can take. The variables are the things that we're choosing in the problem to be just integers, creating an IP, or we can have a mixture of both integers and continuous variables, which creates a mixed integer program, which is also called a MIP. With MIPs and IPs, they're a little bit more complicated to solve, but we can still solve them to optimality. It just sometimes takes a bit more time. Cool. So we can formulate the uncapacitated facility location problem into an integer programming problem. The way we sort of do this is we start with some sets. So here we've got a set of stores, which is I, and a set of possible warehouse locations, which is J. Our data that we have is the cost of building the warehouses, that's B, and then the cost of supplying each store with each warehouse, which is C, and then the subscripts just to note which warehouses or stores. Sorry, in the BJ line, it should be building warehouse J here. Apologies. And we got some variables. So we have two types of variables here. We've got our y variables, which are, these are both binary variables. They can only be 0 or 1. So the y variables are, it's equal to 1 if we choose to build a warehouse in location J and 0 otherwise. And xij is equal to 1 if we supply store I with warehouse J and 0 otherwise. This means that we can formulate our objective to this problem, the thing we want to minimize, to just the sum here of building the stores that we choose, the warehouses that we want to build. And this is the costs of supplying the stores afterwards. I mean, the constraints are pretty simple. Here we just say that each store has to be supplied. So if you sum over all the different warehouses for each store, then that sum has to equal 1, which means that exactly 1 warehouse is supplying each store. And yeah. And then warehouses have to be built to supply stores. This is saying that we can't connect, so this inequality here is saying that our yj, if it's equal to 0, then nothing can be connected to warehouse J. But if it's equal to 1, then you can choose to. You don't have to. That's how that constraint works. Cool. I coded this up. We've picked random locations and turned return square. The connection costs are, equal to the distance between them plus some random value, and the build costs are equal to something else. Here I should show the code for my talk. I'm not gonna do that now because I've lost it. But we use a Python package called Gurobi, which pretty much means you can convert the formulation pretty directly into code to get it to work. And this is our solution for small n. So this solved extremely quickly in about 0.02 seconds. And so you can see that in general, the warehouses are built to cluster around stores, and then the stores are connected to pretty much their closest warehouse, with the exception of a few of them due to the randomness of the cost function, cost values. But if we want to, let's say, have a lot more stores and warehouses, so 300 of each, say, like, the Walmart, then this actually gets very hard to solve. It takes around 4 minutes to solve this. And the solution is, pretty fairly similar. Oh, it's got that random costing again. So the lines do cross sometimes. This isn't great because we increased our problem by a factor of 10, but our time increased by, a factor of 12,000, which is a lot, almost 13,000, which is way too much. And the data we're using actually makes the problem a lot easier. So if we use random connection costs instead of the Euclidean distance-ish of 1, then at the 4-minute mark, this MIP gap, which is how far the computer got towards solving it, is still 13.1%, which is quite large. And that means that it would take, at least 10 minutes to solve, probably even longer to solve to optimality. And so we can think about why this is. So right now we're doing, our formulation has a lot of variables and constraints to handle, allocating each store to the warehouses. We have, n times m x variables and then n times constraints just to do the store allocation. When realistically, we already know how to allocate the stores to the warehouses, Once we have a set of built warehouses, we simply just have to connect each store to the closest warehouse. And that sounds really simple. So we're doing a lot of work in our formulation. We're having a lot of constraints, which slow down, the solution process massively for a pretty easy thing to conceptually solve. This is where we're going to introduce our technique of abstract Benders decomposition. Suppose we have some integer programming problem where the objective is a sort of a mixture of a normal linear objective here, and then the sum of some, more complicated nonlinear functions of big theta omega. So there's a set of these big theta functions, subject to some normal constraints. Each big theta we're going to call a Benders subproblem because we want to solve what these functions are equal to. And then we also have to have a few conditions on it, which is if y star is a particular solution, doesn't satisfy the constraints, then big theta of y star is equal to infinity. That's to make the maths a little bit easier later on. So we can construct something called a Benders mask problem now. So we're going to introduce these little theta variables, and these little theta variables are going to sort of act as estimates for our big theta. So we're just going to start minimizing these little theta variables. The reason we're doing this is because now our objective function is linear, which it has to be for our programs and our solution techniques to be able to solve the problem to optimality. And we subject them to some other cuts here. So these cuts are sort of in the form, you got some normal linear cuts, and then we've got these two sets of optimality cuts and feasibility cuts. We originally keep these empty. If you want to picture what this will do now, sort of unaltered at the moment, is that when we solve this problem, the first time we solve it, it's going to set all these theta variables to 0 because that's going to minimize the objective function. That's obviously not great. So we're going to be adding optimality cuts and feasibility cuts to sort of enforce the estimatory nature of our theta variables. The argument we're going to do this is we're going to solve the Benders master problem, which is this one, to get a particular solution, y star. Then for each subproblem, we're going to calculate what the big theta variable is equal to. And then if it's equal to infinity, we're going to add a feasibility cut to the BMP, which is a cut that's going to exclude that y star from the solution, so it doesn't check it again. And if our big theta is greater than our current estimate, then we need to add an optimality cut, which will readjust that estimate. If we do add cuts, we go back to the start. Otherwise, we stop and we found the optimal solution. Feasibility cuts look like this. Is sort of excludes y variables from the mix. These big gammas and little gammas are just constants. We get to choose them. And optimality cuts of the form, our little theta variable has got to be greater than some linear combination of the y variables. Cool. This is going to make our thetas very bigger, so they're no longer equal to 0, and they actually accurately reflect what the big theta functions are equal to. We've got a few sort of constraints about what the two different types of cuts must satisfy. So a feasibility cut must be illegal for the current y star, which means it must cut off the solution that's infeasible. And any solution that does cut off has to be infeasible. This is where the big theta equaling infinity for infeasible y's comes back into play. And optimality cuts must, be exact at the current solution, which means it has to exactly estimate the value of big theta, and it's got to underestimate the rest, which makes sense because you don't want to be overestimating anything and making it sort of because each of the optimality cards is going to push the big little theta variables up. If we overestimate them at the start, then potentially we can't lower it back down again. So for our back to our motivating example here, we're going to make our objective of our master problem just equal to the build costs plus the little theta variables. We've got a theta variable for each store, and that's going to be estimate the cost of connecting that store, subject to we have to build you have to build at least a single store effectively. That's how easy it is. And then our little theta variables will approximate this minimum store connection cost for each store. This minimation is we go over all of the warehouses and we such that the warehouses are built, and we just find the minimum cost of connection. We have one single subproblem for each store. And for each subproblem, we're going to add the following cut if the actual connection cost is bigger than the estimate. And our connection cost is going to look like this, which is going to equal to the current lowest connection cost minus what the difference would be if another store was built. The reason we add the second part is that it kind of guides the solution into showing what warehouses would be best to turn on next by sort of including on it. This doesn't cover the fact that if multiple stores are built, if more warehouses are built, so just if we build this warehouse as well, how much is the connection cost going to drop roughly? So we can try that again. We run it in a loop effectively. So here we use some random data, so it models the most general case. The Benders ran in 7 minutes and added, a fair few cuts, but the naive MIP actually ran in 40 minutes, which is significantly slower than Benders, which shows that this method is effective for some problems. Problem with abstract Benders decomposition is that we have to invent the cuts ourselves, which is what we did on this slide, which was a little bit weird based on knowledge about our big data functions, which can get very complex as big data gets more interesting. However, if our subproblems are also mixed integer programming problems, we can do a full Benders decomposition, which is a non-abstract type, and we have a closed form solution for the cuts, which is pretty excellent. So this is sort of what it looks like. This is our initial one. We've got split our cost function into two separate sort of non-interconnected parts, and then we can split them up like this. And this means that we can sort of take the second half of these y variables and put them into sub-problems. Since you see that the y variables can be pretty easily sort of extracted from here. So once we have our y star, we can substitute the side of this constraint here, which means that, which means that this is a completely standalone subproblem. So now we go on to duality theory. So we can get the dual of a Benders subproblem, which is this subproblem here, by taking these dual variables u, which is connected independently, and we substitute it to the constraint. So what this does is it takes the right-hand sides of the constraints and multiplies them by something called a dual variable, and then we subject them to this constraint where we have put the old cost function vector here. This is sort of by definition. There's no real motivation between this. This is how the dual proposition works. So we've got this. The dual problem is connected to our normal subproblem by saying that the optimal objective values of the dual and primal problem, which is our original problem, are always equal. So if we optimize one, we should get the same optimal objective value for the other one. And that all feasible solutions of the primal problems is, for all feasible solutions, the objective of the primal problem is going to be greater than the objective of the dual. This implies that this expression here is true. So this is saying that since our cost function for the optimal y variable, the cost function of our original problem, the cost function of our now dual problem is the same, and that the cost of the initial function is always going to be greater than or equal to, for a non-optimal y, this expression here. This is sort of just rewriting this out for the paragraph out for this particular example. And so that this expression here is always going to be a valid feasibility cut if we compare them to the conditions of it. So our theta variable is always going to be bigger than the current dual problem objective. Now, sounds really lame, but it's really important, which means that if we can model our subproblems for our Benders sum problems as mixed integer programming problems, we always have a valid feasibility cut that we can add to the problem, and there's an equally sort of, by definition, valid optimality cut we can add to the problem, which means that we don't have to think about it, and then we can solve a lot of problems with this sort of separability property extremely quickly. Sounds a little bit lame, but it's super, super duper important in the field because it kind of removes a lot of the thinking out of the problem for you. Thank you very much for listening. I've got this picture of Benders here. I haven't watched Futurama, so I like this guy if he's cool, and I don't like him if he's bad. Thank you very much.